the sciences. For this course, that type of time series models covers 3 of the lectures. So it's a fairly small part of this course. And the reason is that we're going to be talking mainly about fitting process models. So that means a model where we have an idea of what the underlying mechanism is. We don't just want to fit a statistical model. We're not just trying to fit the data and then create a forecast, say, or do something else with it. We are trying to understand the underlying drivers of that data. And we often will be, like, we have 2 different models that we're comparing. We're trying to understand, okay, which model is better supported? And we're doing that because those models mean something. Like, one model is that the entire West Coast behaves like one big population, so that whatever we do for fisheries management down in California is going to have some effect on what's happening up in Washington. And so we can't really manage these populations as separate populations. So that might be one hypothesis. And we set our model up in that way. That is a process model. Our other alternative might be that whatever's happening in California is separate from what's happening in Washington. They are completely separate. And so, in fact, they might be so separate that whatever information we have on California doesn't tell us a lot about what's going to happen in Washington. And we need to manage these as separate populations. So that's kind of the sort of questions that we would be asking typically when we're using these models in a fisheries context or an ecological context. And the models that we'll start diving into next week are models that allow us to ask those kinds of questions. Okay, but for today, let's finish up looking at these classic ARIMA models, statistical models of data, and let's see how to fit those in R. So we're going to learn today Box-Jenkins Method. Box-Jenkins Method is the standard series of steps that you go through to fit an ARIMA model to data. Now you're really lucky because we have the forecast package in R, and that's going to automate pretty much all these steps. And it's great. It makes it super easy to fit these models. But you know, whenever you're fitting a black box, you're just sort of typing in an equation, or not equation, you're typing in a function, and say go. You really need to understand what's going into that function, especially for this class of models, because it's really easy to do bad things. Bad things means like you fit a model that doesn't work for your data, and you'll have no indication that it's not working. You come up with nonsensical things. Okay, so first step in the Box-Jenkins method is the model selection. And that has 4 big parts. The first part is evaluating the stationarity. Mark talked about that on Tuesday. We're going to jump in and see, okay, how do we do that in R? And what are the tests that you use to do that? Okay, so what does stationary mean? In the really general sense, it means not changing in time. What that means is it doesn't have a trend, and the variance is not changing through time. I just sort of indicated like it might increase through time, but you can imagine it could be small and then increase and be small again. So we don't want that kind of behavior in our time series. In terms of like the tests we're going to do, typically stationarity is going to mean 2 things. One is going to mean we look for trends, just like a linear trend up or down or an exponential trend. And it means we're going to look for evidence that the data appear to be a random walk. So they're not stationary, so that if you ran it out for 1,000 time steps, it wouldn't just sort of fluctuate around either a line or around some level, but rather it would they'd kind of wander off. Random walks wander off like that if you simulated them a long time. Okay, so let's see an example. We saw this before. This is white noise, right? Here's one. If we do 10 of them and we just keep plotting them on top of each other, they look like this. It's fluctuating around a level. In this case, it's a level of 0. That variance is not changing. Doesn't have a trend. Classic stationary. AR1, where I wrote B, that's actually should be phi up there, where phi is between -1 and 1. So that's another classical example Mark talked about. Here we see it's a little bit autocorrelated, right? It tends to go kind of up and kind of go down. But we plot out a whole bunch of them. We see it's still stationary. So that's one kind of stationary. That's stationary around a average level of 0. There's 0. And it doesn't have a linear trend. But we can also have stationary around a non-zero level. So if we just added an intercept here, so we kind of bump this up a little bit, and now you see it's still stationary, but now it no longer has a mean of 0. We can do the same thing with the AR1. And we could also still call this stationary if we're doing the same sort of up and down movements, but just around a linear trend. So in this case, we have a linear trend here, and we're just kind of going up and down around that linear trend. So what I did to create this data is I started with this. Actually, if you squint, you can kind of see that this is actually these data right here, and then I just said plus a linear trend here. Some slope looks like I used about 0.1 times 1 to 100. I just added that on there. And same with this one. This is actually this data, and I've just added on a linear trend there. These are the 3 types of stationarity that your classic ARIMA stationary tests are going to look for. This will be called your null or your none. This is going to be called a drift or level, depending on the test, and this is going to be called trend. And mathematically, it looks basically like this. You've got your model here that's like an AR1, and then you're going to add a constant there. That's going to be your non-zero mean. And if you add a constant plus you add this trend, so this is some slope times t, so that's like the number of years or number of time steps. Add those 2 in there. But if you just kind of ignore that, this part is the part that we're looking at and looking to see if that's stationary. You can do the same thing with the white noise. Get rid of this thing, and we still have this thing here. So we have this is our level, and then we can add on that linear trend there. Okay, what about non-stationarity? So here's our random walk. Mark showed this. Mark showed these kinds of plots. There, we're plotting a whole bunch of random walks. You can see how they increase. And same way that we added on this constant and a linear trend to our stationary equations, we can do the same thing to our non-stationary equation. So now we could add this, and we could add that. And in the test, what you're going to be doing is, or what the test will do, is they will have this as either your null or your alternate hypothesis, and the other case as your the converse, right? So if this is the null, then the other one's going to be your alternate hypothesis, and then other tests, they switch it around, where this becomes the alternate hypothesis and the other one's the null. But that's how they're going to set up these tests. So they're going to set the test up like that, and they're effectively going to be testing if that parameter right there is 1. Except they're going to set it up, they're going to take they're going to subtract the t x minus 1, put that over there, and then what that allows them to do is the parameter they're testing is, they're testing if it's 0. And now they can do just a linear regression. Okay, the reason I showed you that is because now I'm going to show you graphically what these null and alternative hypotheses look like. And, oh, wait. Okay, yeah, oh, I have a, darn. I have, in the write-up, I have a better plot that shows these side by side. Okay, but let's look here. Okay, so let's go back. So here, look at these. Okay, so this is, let's start here. Okay, so this is, let's say this is going to be our null hypothesis. This would be for the first test we're going to look at. Okay, so it looks like this. It's fluctuating around 0, or it's fluctuating around a level, and it's fluctuating around a linear trend. And now look at the corresponding alternate hypothesis. It's going to look like this. This is the one that is fluctuating around 0. Now when I add that mean in there, or that drift in there, this is what happens. Totally different behavior. It's not a random walk around some level anymore. This will go deterministically upwards. And then now when I have the one where I've added a linear trend, I have that AT in there, it is has this exponential behavior. Okay, so why would you even care? Because when you look at your data and you're testing for stationarity, and your data had an exponential curve to it, but it was otherwise stationary, the test that you use where you said, yeah, keep a trend in there, it will be kind of like, well, it doesn't really seem like it's stationary, but wow, look at that exponential trend. That's a really strong signal. And so it may see the exponential trend in the data, sort of see, and then the test will give you the wrong result because it's being influenced by the existence of this exponentiality in your data. And the reason you have that is that what you actually have is some kind of linear trend, and it would be good to transform your data like with a logarithm and get rid of this thing here. So when you look at literature on how to prepare your data for fitting an ARIMA model, you're going to see a lot of talk about removing linear trends and maybe transforming to get rid of curves in your data like this. And part of that is coming from the fact that these stationarity tests can do strange things if you haven't removed things like curves in your data that are coming from something like, that you need to take a logarithm of it. Okay, so why is stationarity important? If you look at any textbook on fitting ARIMA models, they're going to fit a lot of time in, devote a lot of time to evaluating stationarity. Two really big reasons. One is that these models that we're fitting have, if they're stationary models, and typically we're fitting stationary models, by that I mean, let's say we're fitting an AR1, typically we'll be fitting an AR1 where the B term is between -1 and 1. So if we're fitting that, it fundamentally has this flat level. Fundamentally, it's a stationary process. And if your data don't look like that, you're fitting a model that is inconsistent with your data. We're going to run into this next week a lot, where we're going to fit a model that tends to do this around the flat level, and our data look like that. It goes up, right? And so we're trying to fit a model that wants to go like this, and we're fitting it to data that doesn't do that at all, has no tendency to do that. And it'll fit, but we're going to come up with really bad, we're going to come up with nonsensical parameter estimates. Okay, so that's one big thing. These models are stationary, so we need to make sure we're fitting it to stationary data. Secondly, these algorithms that I'm going to show you today, they're designed for stationarity. They assume stationarity. It's part of why they work really well, is they're assuming stationarity, and they're not going to work well if our data are not stationary, if we haven't transformed our data to make it stationary. Next week, we're going to talk about algorithms that don't assume stationarity. A lot of data in fisheries is not stationary. And these classical methods just don't work for our data. For example, a really common example. Let's say that you had a process that you thought was stationary. Okay, let's think of a density-dependent process. You think, and the carrying capacity is fairly stable. So you think, well, just sort of thinking kind of back of the envelope, what ought to be happening is this population, the stock ought to be kind of fluctuating about some level. I think it ought to be stationary. But what happened is that there was an oil spill, and that knocked the population way down, and the data that you have is as it's recovering from this huge perturbation. So yes, if you let this population kind of run out for a long time, it is stationary. It's a density-dependent process. It's going to fluctuate around some carrying capacity, but it's been knocked out by some huge perturbation, and the data we have are not yet stationary. They're transitory data. So that's one example. Another example would be that your data are, in fact, a random walk. And all kinds of data that we fit are random walks. For example, movement's a random walk. Gene fluctuations, that's a random walk. Population, your density-independent population, that would be a random walk. So lots and lots of random walks that we are trying to work with in fisheries and ecology. All right, but now we're going to fit these classic ARIMA models, so we need to evaluate stationarity. How do we do it in R? So first thing you want to do always is you're going to plot your data out. And you're going to be looking for, does the level change over time? Is it increasing, decreasing? Does it appear to cycle? And you're looking at the variance. Is that changing, increasing, decreasing? Let's see an example with the data you're going to work with. These are catch data from Greece. And we have anchovy here, sardine here. And we can see clearly the anchovy data are not stationary. They have a very strong trend. Is it linear? maybe. Could be. It's a little curved, but that's a pretty short data set, so I doubt that we could statistically say whether that's linear or curved. The sardine, yeah, that probably looks reasonably stationary. All right, so that's sort of your eye test. But like those are kind of nice, actually. A classic thing that'll happen is that you have made a misentry in your data. So you actually have some huge outlier. That happens all the time. Or you entered, when you're trying to transform your data to get it into R, you just kind of mucked everything up and scrambled your data. That seems to happen about, I don't know, 25% of the time when you're first trying to analyze your data. So always plot it out. Always plot it out. Yeah.
Here you only logged it, these ones?
Yeah, these are.
Okay,
yeah.
so you first log, I mean, if you see that there is any kind of like asymmetry or exponential trend, you first log it and then you look at it to check on stationarity?
Yeah. And whatever field you're working in often has some standard transformations they use. In fisheries data, we're using a log transform all the time. But some other fields I've seen other transformations used. Okay, two common tests that you'll hear about whenever you get into these models are the Dickey-Fuller test and the KPSS test. In the Dickey-Fuller test and the augmented Dickey-Fuller test, we're going to be looking for evidence that the time series has a unit root. Unit root is a random walk. So we're looking for evidence that there's an underlying random walk in our data. And the null hypothesis in this test is that it does have a unit root. So it has some random walk component. And the alternative is some variation of stationarity. And that alternative, and the nulls have three versions. Here's the plot that I was thinking of. So here are the three nulls that we have. This is a null, a random walk with no drift term. This is the random walk with this drift term, this is with that added constant. Remember the equations that I showed you? Now it's going to go upward or downward if that drift term is negative. And this one, we have that constant, plus we have this linear trend, which is just some constant times time, and now it looks like it's going upwards. It's hard to tell, but the variance here is increasing because it's a random walk. And all alternatives are going to look like this. There we go, fluctuating around 0, fluctuating around a level, and then fluctuating around a linear trend. In R, the time series, the T series package will apply this test, and you use something called, or what the function is called is just ADF.test, and it's really easy to apply. You can just do ADF.test and then your data. These are the other things that it takes, and you can more or less ignore them. This is the number of lags that are used in your stationarity model. So here I have AR1, but you could have ARP test. You know, so maybe the stationarity isn't AR1, maybe the stationarity is AR3, something like that. So you can test lags up to K. In general, you can just use the default, that'll work okay, and then you want to use, in general, the alternative is stationary. The explosive one is, remember Mark showed you what happens if that B term in your autoregressive is not between -1 to 1? What happens if it's greater than 1? Then the thing starts going bigger. Wow. So it still has the same structure, but it explodes because that B term is outside -1 to 1. So that's what that's about. You can ignore that. So let's look at this for that anchovy data. So one thing to know about this test is that it includes the constant and the trend, always, in this test. So it's okay that our anchovy data are going upward. That's okay. So that's not a problem here. Let's go back here. But what it's saying is that these data, don't look statistically enough like stationarity for us to reject the null hypothesis. And the null hypothesis is, remember here, right? The null hypothesis is a random walk. So the test can't distinguish this right here from a random walk with a constant. That's basically what it's saying. You can't distinguish it from this. And what you're looking for here is, these are the p-tests. So looking at the p-value here, and you would be looking to see if this is less than 0.05 standard level that's used. And it's nice they tell you what the alternative is, because otherwise it's really hard to remember. Okay, which is the null? Is the null that is stationary? Is the null that it's a random walk? So they remind you the alternative is stationary, so we know, aha, we want to reject this. Okay, can't really reject it. We can also do this test with with another package called the BRCA package, and in this one we can specify what type of test we want to do. Could we do a test where we have no constant and no linear trend? Do we want a test where we just have that constant? Or do we want a test where we have both that constant and the trend? Remember, this is the one that ADF test is using. It will always do this one. We'll see this will have an effect sometimes. Okay. This test is, it's a little harder to see if you've rejected the null hypothesis or not, just the way the output is. You have to get the test, and then you need to look it up against these test statistics. It's a little tedious. You're going to do that in the lab, and you'll see. It's not too bad. Basically, you're going to look at your output from the test, and this tau is what you're looking for. This tau is that parameter that you're, it's referring to the parameter that you want to see is it different than 0? And you need this test statistic to be less than your critical values. And you're looking at the 5% critical value, and you can see negative 3.45, it's just above 3.5. And that's what we saw in that other test. We saw that it was like 0.07, right, just above 0.5. Okay. Let's look at the next test that you're going to hear about. It's the KPSS test. In this one, the null hypothesis is that the time series is stationary. Okay, so this one, you don't want to reject the null. You want to accept the null. This is what I was saying, like when you apply these different tests, you're going to be like, which one is it? This one's nice in that the stationary assumption is general. It's not going to assume like a particular type of AR process. And this is how you apply that test in R. You're just going to say KPSS test. you apply it, and you can have either, you have those three options again, null, sort of none, level, or trend. And to here. So this one, we do reject the null hypothesis of stationary. That's not what we want. Okay, so when people are sort of digging deep in their data, trying to understand whether they can accept stationarity or whether it has evidence of stationarity, they're going to run both these tests because it's a nice thing that the nulls are different. Because one, you're going to tend to, right, the criteria of 5% is quite stringent, right? So one, you have the stringent criteria to accept the null, and then accept a random walk, and then the other one, you have the stringent criteria to accept stationarity. So they kind of complement each other. So you want to do both of them, and in this case, the test support non-stationarity in the anchovy time series. So both of them supported that. So we know, okay, we have to do something with this anchovy data. We can't just plow ahead and fit a ARIMA model right to the data. Yep.
So how common is it that they actually have different results?
No, they have the same result.
Okay, like this.
They're both rejecting the hypothesis that the data are stationary. They're both saying there's not a lot of data support for stationarity. Or they're saying, we can't reject that it's not a random walk.
Do they ever have differing? One of them is sometimes says stationary while the other one says non-stationary.
Yeah, that can happen.
In that case, you just kind of like throw your hands.
Well, in that case, if you're being cautious, you would say, okay, well, I still ought to do something to deal with stationarity. It's pretty easy to deal with it. You difference your data. So it's not that hard. I should back up when I say it's not that hard. It's not that hard in these kind of nice data that you're going to see in textbooks and in the examples that I'm going to show you. In the real world, when you're trying to apply this to data that you have collected, maybe for your thesis, you will certainly have issues that can't be dealt with a simple differencing. So what are some examples of that? This issue where your variance is changing like in different parts of your time series. So it's really low variance, really high variance, and really low variance again. Like that's something that's hard to deal with a simple transformation. So I mean, it's easy enough if like the variance is increasing as this as your counts get larger, right? So that would be dealt with by something like a log transform. But what if the variance didn't seem to have anything to do with like the size of the counts? It was just like the variance was really high in the 60s and it was low in the 70s and high in the 80s. And you plotted that variance against the size of the counts. So like when I say the size of the counts, like are your counts like 10 or 1,000, something like that. But you saw no pattern. And now you got to do something else. A simple transformation isn't going to fix that problem. And what might be going on is that you have kind of different regimes. There's a lot of, like you're working in the real world, you're working on the ocean, there's a lot of things that are changing in the ocean that you're not tracking. And people use, typically what I've seen honestly is some kind of ad hoc transformation. So either you're using an ad hoc transformation, so by that I mean they do a transformation where, okay, let me give you another example. So instead of the variance, let's talk about level. Let's say your data looked like this, and that's the 1970s, the 1980s, and then back here 1990s. Okay, your levels are jumping all over the place. But otherwise, within a decade, they're looking all right, right? They're looking kind of stationary. So you got to get rid of that jumping around like that before you could apply an ARIMA model. So what people will do is they'll do something like, you might estimate a level for the different decades, and then you remove that level so you kind of line everything back up. So it's kind of like an ad hoc transformation. That's one thing. Another thing that people do is they'll say, all right, I'm just going to analyze my data in Windows. Looks like the 1960s. Looks like I can assume that that's stationary, or I can just do a first difference and make it stationary. So I'm just going to analyze the 1960s separately. I'm going to analyze the 1970s separately, 1980s separately. So those are the most common strategies I've seen. Yep.
When you're choosing what your null is that just based on like based on looking at the data and saying, okay, this looks like an exponentially increasing thing, so we'll choose trend? Or do you always choose trend?
Typically, you would always choose trend unless you've done something that will remove the trend. We're going to see that in a moment. Okay, so the standard way we're going to deal with stationarity is we're going to difference our data. You saw this on Tuesday. This is your first difference here. We're just going to subtract these two, subtract those two, those two. So in this case, the first difference would be 1, 2, 3, 4. That's 1, that's 2, that's 3, that's 4. Second difference would be you take the difference of the first differences, and then in this case, this becomes 1, 1, 1. You don't really see differences greater than 2. And I think typically I would say I only see first differences. Or at least that's the most common ones that I would see. So let's look at that for the anchovy. So there's our anchovy. And here's the first difference. And that looks a lot better. First off, we got rid of that trend, which is great. And which is what a first difference will do. And now it looks like it's kind of fluctuating around the level. It's not quite 0. It looks like it's almost 0, but it's actually a little bit above that. And now let's test the stationarity of this. So we're going to take the difference, we're going to put that in something called diff anchovy, and then we're going to do the test. And for the KPSS, the null hypothesis is stationarity. We don't want to reject that. And now when we do it on the differences, we don't reject it. So that's great. That's what we want. For the Dickey-Fuller test, the null hypothesis is a random walk, and we want to reject that. Ah, darn it, we didn't reject it. Okay, well that's not good. However, remember I told you that that first difference is going to remove the trend. So we just used a test that includes something that we just removed. It includes a trend, and we removed that trend. And so we have estimated this extra parameter. So our test is much weaker than it should be because we're including something that we have in fact already removed. So we don't want that trend in this ADF test. With ADF, it will always include the trend, but you can use the URDF and remove that. The type drift, so instead of saying type trend, you say type drift. That removes that trend. So it only has that constant. What that means is it only has that non-zero level. And you're looking at this here, and you'll see that this is now that I removed the trend, I made my test a lot more powerful, and this is -5, and that's well below the 5%. So now once I use the appropriate test, everything worked out. Okay, so you're probably thinking, oh my God, how do I remember this? I think this all the time. How do I remember all these tests? Fortunately, like I said, the forecast package is going to automate this for you. And there's 2 functions that you can use. The first one is this thing called indiffs, which is how many differences do I need to apply to my data to make it stationary. And you can choose either the KPSS or the ADF. You can try them both, see if there's any difference. In this case, there is no difference. This is using the augmented Dickey-Fuller, but it knows that when it takes the first difference, it knows to remove that trend. If you took a second difference, it would know to remove the constant also. So it's smart that way. You don't have to remember to do that. It does that for you. And it tells you that you need 1 difference to make your data stationary. So how would you use that? Well, you know those tests that you're looking at, like the ACF and the PACF, for those tests, you want to apply that to stationary data. So now, when you want to do those visual tests of plots like that, you should apply it to stationary data. And so you know, oh, okay, I should do that to the first differences. And you have a reason to have chosen that. Okay. Okay, summary. Looking at your data and thinking about stationarity in your data. Always the first step, plot your data out and just get a feel. Does it have trends in it? Does it look like a random walk? Next thing, apply unit root test. And these are the 2 tests. And then if it fails those, you apply differencing. Still fails, try some second differencing. And then if it's still not passing, then kind of rethink, is this really what you should be doing, or you've got some other issues in your data that you shouldn't just blindly apply this type of law. And as I said, these steps are automated by the forecast package. So next step, in the Box-Jenkins method, we need to select our model. We need to select our AR level and the MA level, and we need to estimate those parameters. On Tuesday, you learned how to use the ACF and the PACF to get some insight into the structure of your data and what ARIMA models, what AR and MA lags might be appropriate for your data. As I just mentioned, you want to make sure that you're doing this to stationary data. So you're going to figure out what differencing or what other kind of adjustments you need to make to your data before you start looking at this. Okay, so that's kind of a nice visual, and you should definitely look at your ACF and PACFs to see if there's anything weird going on. But when we actually select these for a model that we're going to fit, we're going to use some type of formal model selection. So what this does is it weighs how well the model fits against how many parameters your model has. And there are a number of different information criteria out there. The ones that are used by forecast and by ARIMA, underlying function, which is ARIMA, are AIC, AICC, and BIC. AICC is the default criteria that's going to be used. And so what this function is going to do is it's going to fit a whole bunch of ARIMA models. Actually, it's ARIMA models. So it does. ARIMA means it has the differencing. It's going to try different differencing. And it will fit that model, compute the AICC, and then it'll fit another model and compare the AICC to that model. If the AICC is smaller, it'll choose the new model, not going to try something else. So it's going to do this search to find a ARIMA model that has the smallest AICC. So that's a basic idea. And you can do this yourself, kind of like come up with a whole bunch of ARIMA models, fit them all, and then make a nice table with the AICC. But this is going to automate that for you. So let's see how this works. Here, I'm going to do that with the anchovy. Okay, before I go further, I want to say something about the syntax up here. Do you notice I have forecast ... auto ARIMA? The part before the ... is the package that the function comes from. In your own code, you can use like library forecast, and then you can just call auto ARIMA. For the class, for the things I present to you, I'm going to try to always put the package ahead, so forecast ... because otherwise you just get lost. I'm using like 6 different packages. You're going to get lost in which one it's coming from. So try to always remember to do that. And that's what you're seeing there. Okay, so if we fit that, this is the output. It selected that best model had one difference. We knew that, right? We already ran in diffs, and we knew that that's how much differencing we needed to make our data stationary. So that shouldn't surprise you. So this is the order of the AR part. That's the number of differences, and that's the MA part. So what it's saying is that the model that was selected with the lowest AICC had no AR parts and one difference and a lag of 1 for the MA part. And then it gave you your estimates. It says with drift, that means that it has a constant in it. That means that your first differences don't have a mean of 0. They have a non-zero mean, and estimate what the correct mean is. That's what it is.
Hey, Eli.
Yep.
Did you, so you applied auto ARIMA before you first differenced it or after you first differenced it?
Oh, you don't have to.
You don't have to
You
do
have
it
to
at all.
do that. No, it automates everything.
That's what I thought.
Right, and so, but now when you look at this and you see, like, hey, it first differenced my data. Why did it do that? You know why it did it. It did that because it had to make the data stationary. It selected that differencing ahead of time before it's going into the part that's estimating the AR and the MA part.
Yep. Will it fail if it can't make it stationary according to those like criteria for the test, or will it just output the best model?
It will output the best model.
Okay, so you need to check beforehand.
Yeah. Yeah. Definitely. Yeah. Okay, so this function, it needs to search all these models, and by the default way it's going to do this is stepwise selection. And we can change that. We'll see later. We can turn that off. But let's just leave stepwise selection on there. And we want to see what models that it fit. And it's showing us the models that it went through. So these are the ones that it went through. And this one has the lowest AICC. This, that's the model, obviously, and these are the AICC. So that's the information criteria that it's using. We can change that information criteria to something else. We could use BIC or AIC, the other options. All right, so this is the model that it's settled on. So we have that first difference, we have that constant here, and then this is our MA with lab 1. All right, so now what I want to do is show some other examples with some simulated data. You get kind of a sense of how well this works. So we can simulate some AR2 data using the ARIMA sim function. And okay, so back up just a little bit. You notice ARIMA sim doesn't have any ... in front of it. That means that it's just base R. In this case, it's stats, but stats is part of base R. Okay, so we have the n number of data points, and then our model is a list that is the AR part and the MA part, and in the AR part is just the order. So this is your first AR part, so it's the number that's going to go in front of x t minus 1, and then the second is the lag 2, so that's the part that goes in front of x t minus 2 in that equation. I constantly forget the syntax for ARIMA sim. Unfortunately, all these functions, they have slightly different syntax, so I am constantly doing question mark the function name to remind myself what the syntax is. So if, like, your head is swimming, it's like, how do I remember that, the syntax? You don't need to remember that. You just do question mark and look at the help. Okay, so that's some simulated AR2 data. And then I can pass that into forecast. And, I added on some extra stuff here. Ignore the seasonal part there. Ignore that. This max D here is, I wanted for this example, I wanted it to work a little better. And I knew that I didn't want auto ARIMA to consider differencing my data. Because I knew what data, I knew the structure of the data that I created. There will be situations where in your own data, you might want to limit the differencing. Here I said don't consider any differencing. Don't fit those kind of models. In your own data, you might also be in that situation where you don't want it to difference the data. I just want you to find the best model without any differencing. And you can force it to do that by doing that. You could also say don't consider any differencing greater than 1, for example. You can do the same thing with your P and your Q. So for example, you want to fit only an AR model. A common thing that we would want to do in fisheries is to not consider MA models. And you can do that by saying max Q equals 0. The Q is the MA part. Just say don't consider those models. So in this case, I didn't want it to consider differencing. It's just going to consider AR and MA models with no differencing. And you can see here, this is the model that it estimated. And you can see it's a little more simple than the actual data. This actual simulated data was AR2. It said the AR best model was an AR1. We could do a little simulation and see how often the true model is selected. So this would be 100 simulations, 1 to 100. And I'm just going to, in this for loop, I'm going to create this simulated data, that structure, and then I'm going to fit it, and then I'm going to save the data as a little text, and it's going to have the ARIMA size. So this part of the fit is going to be like it's an AR1, AR2, AR3, AR4, etc. And this is going to be, the second part is the size of the MA product. So this is basically P, and that's Q. So if it said that the best fit was an AR2 with no MA, what would this look like? It would say 2-0. If it estimated that the best model was an MA2 with no AR, it would be 0-2. So I'm just storing this so I can look at a whole bunch of models that were selected. And now I'm going to make a table. So what you see is that when I simulate this AR2 data, it's overwhelmingly, it's like always, picking an AR model. That's good. This was an AR process. It's not an MA process, so it got that right. But it's pretty much always selecting a smaller model. So it's an AR1 and not an AR2. I run these kind of little simulations all the time when I'm starting to work with my data and I'm trying to understand, okay, well, I've got 30 data points. How complex of a model could I estimate? And this is like one of the most common questions that I get from people. Is 10 years of data enough? It entirely depends what you want to do. If you want to estimate an AR3 model, then no, 10 is not anywhere near enough. And I could easily show you that by running this and putting 10 in here instead of 100, and you would see the estimates are just all over the place. Here I'm just looking at the structure. You could also do the same thing and record the parameter estimates, and you could get a histogram of what the parameter estimates look like. So that just gives you, it's a really handy way to get a sense of how much data you need, how well you can estimate these parameters. You do have to come up with the parameters for your simulation, but oftentimes you'll have a guess, or you can do the simulation and be like, okay, no, that variance doesn't look about right, or that looks too small. Just kind of play around with it. Okay, I told you that the default it's going to use stepwise selection. So it's not going to look at a whole huge suite of ARIMA models, but you can turn that off, and you can say, I want you to look at many. Just look at every single one within kind of reason. So that might be within like a size, a lag of 5. So up to an ARIMA 5, and so AR lag 5 and MA lag 5. You want to look up to that size. So all you do is you say stepwise faults. You don't need to care about that approximation here. You turn off the stepwise, and you could turn on the trace, and you could look at all the models that it used. What I'm showing here is what you do in your final step. When you've you've decided, you're done with playing around, what you'll do is you'll turn off stepwise to do an exhaustive search, and you turn off some approximations that it uses to speed things up. If you have a whole lot of data, tens of thousands of data points, this could take a long time. For fisheries data, it's not gonna, we're usually like 100 data points, we're pretty happy. But if you had hydrophone data, right, exactly. Okay, so summary for the model selection and fitting with, so basically, once you've dealt with stationarity, you're going to look at your PACF and your ACF just to get a sense of your data, make sure there's not anything really weird going on. And then you can use auto ARIMA, and that will automate this whole step of searching the different ARIMA models and selecting one. I showed you how to use trace, and that will be especially important when you don't want to select just one model, or you want to see if there are maybe a handful of models that basically fit the data almost as well. So you look at the AIC, it was like negative, 3.65. Well, maybe there's another one that's negative 3.5. Well, then you'd want to keep both of those in the running. Consider both of those. There are situations where you're not just going to use the model that is selected by auto ARIMA. In fact, you might not do a search for a model at all. The most common reason is because you're using an established model. Somebody else has been using this model for catch data, catch forecasting. Everybody accepts that this is the model we ought to be using. You're going to use that model. Maybe that's an AR2 model. Okay, so you're just going to use that model. So in that case, you don't search. The other reason is that there is some fundamental reason that the data should be an AR or an AR with an MA process. Example, you're looking at movement data. That is fundamentally and generally speaking an AR1. I'm here. Where I step to the next moment depends on where I was. Doesn't necessarily depend on where I was standing, 5 minutes ago. Okay, so those kind of hop processes are fundamentally AR. Okay, last part, model checking. So basically, you're going to be looking at your residuals. In a ARIMA model, the residual is the difference between your expected value given the data up to t-1 minus the actual data at time t. This is different than what you would have in a linear regression. So in a linear regression, you would predict the value at time t from all your regressors. That's your prediction. You would have the data at time t made minus that prediction at time t using all the regressors at time t. So the ARIMA model is a little different because you're only going to use the data up to the previous time step. This makes, when we plot, I think I have a picture of this, of plotting a fitted value against the actual values. They always look a little funny from a ARIMA model, and it always looks like they're a little bit staggered. Like you have the actual data, and then your predictions they look like they've been shifted one off. And they're shifted one off because they only use the data up to t-1. That's okay. They're supposed to look like that. R makes it really easy to get these residuals. For any type of fit that you do in R, you'll have this function residuals. Boom. There is this standard function residuals, and package makers make a version of this for their model. So you can just pass in the fit, and it will give you the appropriate residuals. So here's the residuals that come from our ARIMA fit. The fitted is the other thing that you'll often need from models. So this would be the expected value at time t from your model. So that's fitted. Again, you can use this for all types of model fits. Linear regression, you're going to see it for the state space models we're going to start digging into next week. So the standard kinds of tests that you're going to do, you're going to plot your residuals. They have to look like white noise, roughly. You're going to look at the ACF. Your residuals should be uncorrelated. You're going to look at a histogram. It should match whatever your error assumption is. The models we use assume normal errors, so they should look fairly normal. Again, forecast package makes your life a lot easier. You've got this function called check residuals. You just do check residuals fit. This is the thing that needs to look fairly like white noise. If it's got a big trend to it, if it's got a big hump to it, that's bad. Don't want those kind of things. This, when all these lines between the blue, it's autocorrelated, it's not correlated, and this should look roughly like this line here. It doesn't in this case because we don't have a lot of data, but it doesn't look horrible, so it doesn't look bimodal. Horrible would be, right, two peaks over here, that's really bad. Probably if we had more data and it looked like it had these little humongous tails, that would be bad too. Check residuals does the standard test for you. This test is the test for autocorrelation in your residuals. This is the one that's used for time series residuals. And it just does it for you, picks the right number of lags, adjust the correct degrees of freedom. Nice. And we don't want to reject the null for this. This one's kind of too bad. It doesn't tell you what the alternative is. So you have to look, if you forget what the null is, you have to do question, check residuals, and look that up. But you can see here, I mean, if you just look here, you see something like that. Good. That looks good. I also like the check residuals when I'm doing a model that doesn't have a nice little function like this. I'll use this and I'll remind myself, okay, right, those are the plots I should make. If I do those three, I'm generally pretty good. Okay, so let's jump into, I'm going to do 2 minutes. I get to see if I can get through the forecasting. And then we'll go into the lab and I'll talk about working with some seasonal data. So the basic idea with forecasting is super easy. Basically, we're going to estimate a ARIMA model or an ARMA model. So if there's no differencing, say, it would be ARMA. So we estimate that model. So we're going to have these parameters. And we're just going to forecast into the future by using those parameters and the prior data. Okay, so the model that has a constant in it, actually the way they're going to write it is going to look like this. Mark mentioned this, that you have this kind of M here, so instead of having that mu there, they're going to write this, write it like this with this M, and then if you need to solve for a mu, you have to do this. I'm showing you this because in fisheries and ecology, we always write it like this. In a lot of the textbooks you see, it's going to be written like this, and then you go into R and fit it, and it will do this form, and I have wasted and myself and many other people have wasted many hours trying to figure out why on earth they couldn't reproduce the forecast when you put in dutifully the estimated intercept. You don't get out the right answer, and that's because they write it in this form. Okay, so basically, let's see an example with the anchovy.
There's a quick question from Newport too.
Yeah.
So folks would like to know if you start with the kind of a biological rationale for doing the data mining tests for different AR processes, or whether you whether you use the test to look for biologically meaningful lags.
Depends entirely on what your objective is. So if you're doing catch forecasting, typically you're trying to find a statistical model to use for a forecast. And that model does not itself have a biological meaning. You might infer a meaning from the model, but the objective is really just to come up with a good forecast. If you're using the model to understand the underlying biology and the mechanisms, the processes, then definitely you would be looking at the lags and trying to understand, or you're probably looking for particular lags. For example, you have something that has a very strong 2-year life cycle.
Pink salmon.
Pink salmon or something, maybe it's not quite that strong, right? Yeah, anything else not quite that, but it's still strong, so that you expect to see an effect, say 2 years prior, or let's say Chinook, okay? It's where you ought to see these like 5-year lags, 4 or 5 year. And so because of biology, you would look particularly for those lags. So.
I think, yeah, that's very good.
Okay, so let's see an example. We fit this model, so that's the model, and then we want to forecast. So basically, we're just going to forecast with this right here, and I put in those estimates. That's the lag 2, that's the lag 1, that's the mu, which I've calculated here using this equation right here. This is that drift term, so I do the drift times 1 minus the 2 slope terms. And if I want to get our forecast for 1990, I'm just going to plug and chug. I've got, this is what the equation should be. So just that YT is the first difference, because it told me that the best model was a first difference model. So I've got that here, here, and now I'm just going to move things around and solve for 1990. There's the R code to do that, and boom, there's my forecast. It's rather tedious. Fortunately, forecast does all that work for us. With forecast, you just do this, say that fit, forecast, how many steps in the future, and it prints out our forecast, and it also gives us our prediction intervals. I'm going to talk about prediction intervals later in the course when I talk a lot more about forecasting, forecast evaluation. And you can see this number here that I computed here is the same as what you get right there. Another really nice thing with forecast is it does the plots for you. So you do that forecast and then you say plot, boom, you've got your forecast and you have the prediction intervals. Very nice. Missing values, somebody brought that up on Tuesday. These functions all work fine with missing values. Let's see an example with the anchovy. I'm going to take the anchovy and I'm going to put in a whole bunch of missing values in there. And you can see I can still fit the model. I can forecast with it. I come out with a forecast. Let's plot it. Here we go. Look at all these gaps. Now, if I put too many gaps in there, obviously it's going to struggle to estimate anything. But the actual math, the algorithm, chugs along just fine. It gives me my forecast. Okay, let's take a break. I'll finish up with the seasonality of, show you some forecasts for seasonal data that you can do with R, and then we'll let you get started on the lab. So let's say 10 minutes? Yep.
Yeah. might pick you up on that. Are you going to? I have to write email. Just like a small coffee would be great. Thanks for you willing.
So, Mark,
Yes.
there was a question online about looking,
Did you pause?
oh. Hey everyone, we'll be back in 10 minutes. Now more like 8.
This conference will now be recorded.
Okay, so I want to touch briefly on seasonality. The whole part of the lecture I've talked about this landings data that's annual, doesn't have a season, but oftentimes we do have seasonal data. For example, this is the monthly Chinook landings in Washington that I downloaded from a state website. And it looks, it's a data frame and looks like this. We've got our year, we've got our month, species, and then we have our log metric tons of landings. It's very helpful to put monthly data into a time series object because then you can easily plot. If you've ever tried to plot out seasonal data, trying to get the axes correct is really frustrating. And if you make that into a time series object, it becomes trivial. And it's really easy to make your seasonal data into a time series. You want to make sure that you haven't left out any data. So that means if you have monthly data and say you missed March one year, you don't go from February to April. You don't skip March. Instead, you have March and you put in an NA. March is missing. So you don't want to miss any months. Once you have that, so you have, this is a vector of the Chinook landings for every single month. Starts in 1990, goes to 2015. And you just do TS and you tell it what the start is. And when you have seasonal data, you need to tell it what, in this case, month it starts on. So frequency 12 would mean months. If it was quarterly, you'd say frequency is 4. You could have frequency equals 3, 24 or hours. And then here it starts in 1990 and in January. If the data started in February, I could do 1992. So that's it. You've created this time series object with the season information. And now when you do plot, it nicely has the years. And then the months are then within the years. If I had more tick marks, it'd be clearer, right? So this is somewhere around here. This is about 2014. And you can see there is quite a seasonal trend here. Low in the beginning of the year, and then it's high in summer. No, it shouldn't be surprising. This data set has a big gap, 2000, 2014. I'm not sure why that is, but it does. And we can fit a seasonal ARIMA model to these data. So the basic idea for a seasonal model is you're going to have, first off, some differencing. Pretty standard that you're going to subtract out the, or you're going to take a seasonal difference. And what that means is you have your data at time t, and you're going to subtract the data at time t. Oh, that ought to be minus. So it could be, well, it's going to be minus. You subtract the data in the past. So that's minus s, and s is the season. Okay, so what that means is that would be January 1990 minus January 1989. February 1990 minus February 1989. So you're just subtracting the data from the same month the previous year. That would be a first seasonal difference. So typically, you're going to be working with data with that first seasonal difference. And the basic structure of these models is that you're going to have this AR part that is going to look just like what we've been working with. So you're going to have the ZT, which is the seasonal difference, is a function of the difference in the previous year, maybe the previous 2 years. So the previous 2 years would be an AR2 year. So you have that part. That's called your non-seasonal part. And then you have your dependency on past seasons. So that's your AR part from the season. So what does that mean? So that means that my value this year in January might be a function of the value of January last year. So that's where you have this auto regression from a whole season prior. You imagine with Chinook, say pink or something, that we ought to expect that kind of seasonal auto regression. Or it shouldn't surprise us to see that. The way the math works out, you will also get this part here because you've got this dependency on last, so say that you have this January and it's AR1 in the season, so you're going to have this January depends on last January, but because you also have that this year depends on, it's not last year, it would be that January depends on December. It's one data point prior. That's what this part is. There's no season here. It's just like January depends on the December depends on November. That's what that part is. You've got that in here. So what that means is that you also are going to end up with this part that says that this January depends on last January and on the month before last January, so the December 2 years prior. You don't have to worry or think too much about those details. Just, I think the main point is to realize that you've got these two components to this seasonal model. One is going to be depending on the prior year during the same month or the same season, and the other one is going to be depending just on the prior month. And the way we write these models, the notation that's used is this. The first part is that non-seasonal part, and this part is the seasonal part. And then this tells you how many time steps there are in each sort of year, or whatever your larger time unit is. So this 12 would mean, if it's yearly data, it would be this monthly. If it's 4, it would mean this quarterly data. Okay, so how do you read this? Just reiterate. Let's start here with the seasonal part. It would say, okay, we're going to do a seasonal difference. So we're going to take our data and that Chinook data, and we're going to subtract off, we're going to create differences where we have this year minus the data last year in the same month. So those are the seasonal first difference. That's the data that we're going to work with. We're not going to do any other differencing on top of that. That's 0. And now when we look at the seasonal part, we've got a 1 here. We have a 0 there, so we have autoregression of 1 lag. So what it's saying is that the Chinook catch this year in January is a function of the Chinook catch last year in January. So we have some seasonal effect. And then we also have this 1 in the non-seasonal part. So it says also that the Chinook catch in January of this year is also a function of the catch in the prior month in December. So it depends on 2 things. The data 1 time step prior and the data in full season prior. Don't worry about that part. Just concentrate on the main things here.
Would there be cases where it's best to just like remove the seasonal component, like you would remove like a mean trend or something, as opposed to modeling it via this like seasonal ARIMA model?
So that seasonal difference removes that trend, removes that season, removes the season.
But it's still dependent, like the AR1 process on the season before, right?
You could, so you've removed the season by doing this difference.
Right.
And then when you fit the model, you could tell it, don't consider seasonal models. You could do that.
Is there a benefit to doing it one way or the other?
There's a benefit to trying the seasonal model if you're working with seasonal data, because you often would like to know if there is an effect of prior years. I mean, typically. However, if you're working in a situation where you know that last, like whatever the landings were last January, shouldn't have any effect on this year. I know that's not what's going on, but there's no biological reason that would be the case. Then, yeah, certainly you tell it don't consider those models. So I guess that would be the reason. If there's some biological reason that a seasonal lag shouldn't be included in your model, then that's a good reason to not allow those types of models to be considered. So let's see how we fit this in R. What I'm going to do is I'm going to fit to the data up to, that's 2099. I'm going to fit to these data here. Okay. And then I'm going to do a forecast and compare my forecast to the actual data. So here's what that code is going to look like. First, I'm going to set up the data I want to fit to. I'm going to take the Chinook time series. I'm going to use this function called window, which is going to take a segment of that. And that should not be a 10. Why is that 10? Oh, it must be that it starts in October. So this is the first data point, and this is the last data point I want to include, so 1998 in December. And my test data is what I'm going to compare that to, and this is 1999. So if I were to now type trained at you would see a time series that just goes from October 1990 to December 98. And I fit that just like that. I don't have to tell ARIMA to consider seasonal models because it recognizes that this is seasonal data because it's a time series object. You can see that the frequency is not 1, it's 12, and it will by default consider seasonal models unless I tell it not to. So to fit that, and it estimated this seasonal model. So what does this say? It said that it removed the season. There was a seasonal cycle. We all could see that there was a seasonal cycle, and that differencing removed that seasonal cycle. So that's what it did. However, there was no effect of the prior years. And you think, well, why did it difference it? Well, because we remember we need to fit these models to stationary data. We need to get rid of things like these big cycles. And this is what got rid of that big cycle. So that made our data stationary. We didn't have to do any other differencing to make our data stationary. We just had to do that seasonal cycle, get rid of that seasonality. But once we got rid of that, there was no further effect of season. So the value of the catch last January is not affecting the value of the catch this January. Thinking about Chinook, you might think, wait a second. I mean, shouldn't this is a species, it's reproducing. Shouldn't there be some effect of prior years? Yes, but probably not in the month, right? It's not January, that January affects January. It's the month where you see all the spawners. That month affects future months. Right? So if you had a lot of spawners this year, you would expect in Chinook 4 or 5 years later, you're going to see a lot. But it's not the January that's important, it's the month when they're spawning. That's something to keep in mind when you're interpreting this. And you think, well, why don't I see a seasonal cycle? Well, remember, it's only, if it's monthly data, it's looking at the effect of the Januaries on the Januaries, Februaries on the Februaries. And so you might have to set up your seasonal model very differently if you're looking at a species that reproduces at one particular time of the year. Or perhaps it's you think that it's when the fish are going down through the river and you have a critical a critical time, and if they experience a lot of mortality in that time, that has effects in later years. But it would be a particular month during the year. Okay, that was an aside. So anyhow, with the Chinook, it's not that the Januaries affect the Januaries, which actually makes sense. However, the value of the catch this month is influenced by the value of the catch the previous month. Or more precisely, the value of the catch in the previous month has some information about how large or small the catch this month will be. That's the more accurate statement. So if I'm doing a forecast, knowing what the catch was last month gives me some information. Okay, so we got all that just from one line of code, and then we can plot that out. So we do a 12-month forecast with that line using the forecast function. We can plot that forecast, and that creates this, and it puts that blue line in there, and then we can add points and add the test data. So you can see that there's actually a lot of predictive value here. There's this really strong seasonal cycle, and we can use that seasonal cycle plus the sort of general level that the landings are at to get a pretty good prediction of what the landings are going to be next year. Missing values were no problem. Notice we had these missing values. That's just fine. Be kind of actually an interesting exercise to start blowing holes in that data and seeing how many missing data points you can get in there and still pick up that seasonal cycle. I'm guessing you can probably remove a lot of the data, especially if you removed it randomly. Yes?
It's kind of a side comment, but once I blindly did a seasonal ARIMA model on some hydrological time series,
Yeah.
turns out that you can't have a fitted on anything that has a seasonal component of over 200 or something. So if it's like daily data and trying to get a yearly cycle, you just won't fit it. It's not possible. So actually, they use, Rob Hyman uses like 48 time series on that.
Okay.
But the auto ARIMA will just crash.
Okay.
Daily data. Not cool.
Yeah, interesting. That's kind of strange because I wouldn't think that it would matter.
I wouldn't have thought so either. Why would you care?
Why would
You
care?
can do it yourself. Once you have the model, all you have to do is generate the innovations and you could forecast from it.
Yeah, I think a lot of it is just memory issue.
Maybe.
Oh, interesting. Okay, so you can't do it daily. Okay, so the summary is forecast is your friend here. It makes it really simple to fit those seasonal models. And differencing. You want to plot out your data, and if you have season and no trend, generally speaking, you're going to do a first seasonal difference. So you're just going to subtract off the, you're going to take the difference between this year in this season and last year in the same season. If you have a seasonality with a trend, then, or sorry, if you have no seasonality but you have a trend, generally first difference be used. If you have both of them, then you're going to have first a seasonal difference, and then you take the first difference of those. Neither, no differencing. If you had a random walk, you would use a first difference. And then if it's something parametric looking, so that means like something that looks like that, then some type of transformation, like a log transformation, typically be what you use. And if it's, as I said earlier, if it's something that looks really wonky, then you're in the territory of ad hoc.
What about